we go. Okay. So, hi everyone. Glad to be here. Today I'm going to talk about a generic approach to secure and massive IoT device factory provisioning. So, starting with, my name is Mieszko Mieruński. I'm working as an embedded team lead at AVSystem. Previously, I've been contributing to the Zephyr project in peripheral drivers, mostly for Nordic chips. Biggest achievement there was driving the UART API changes to allow for efficient asynchronous operation. And currently, I'm focusing on the IoT protocols, mostly lightweight machine-to-machine. And I wanted to thank my team, especially Michał Zając and the whole team. It was a joint effort on getting this provisioning flow running. So, what I'm going to talk today, at first I'd like to provide some background information on why this topic is important to me. Then a bit about device provisioning in general, like what are the methods and used, what has to be considered here. From that, move on to the lightweight M2M bootstrap interface, why we decided those solutions based on that and how to use it for generic cases. And finally, the factory device provisioning tool that is available in our library and how it integrates with Zephyr itself and how it could be used not only for lightweight M2M devices. So, a short introduction. For AVSystem, device management is the core product since the beginning, starting 60 years ago with telcos and expanding to Wi-Fi and IoT solutions. Currently, company offers 4 groups of products designed for different verticals. With the releases of Android IoT SDK and Coiote IoT device management server, we became more and more focused on the embedded community and started proposing new solutions based on our previous experience. The most interesting part here would be the Zephyr module, which enables the most complete lightweight M2M implementation on all Zephyr devices, as well as Zephyr client, which showcases functionalities like firmware of the update or Edge Impulse integration and more. So when talking about IoT device management, we also have to talk about the device lifecycle management. Even before starting the production process of a new device, we should think about its whole lifecycle, starting from the factory, deployment into the field, and ending with the commissioning. All activities should be monitored and planned to prevent security risks, and also to think about the environment to not produce more waste. Whole process can be further split into smaller steps. I'm not going to go into details on that here, as the topic is just large and would need another presentation for it. But the first step is what we are going to focus now, so the device commissioning and how the device is actually provisioned. So what actually is device provisioning? It is a process of configuring both device and server so that the device can start its normal operation. When doing it at a bigger scale and designing the whole process, there are some things that should be considered beforehand. So what are the security measures? Is the process safe? Does hacking one device compromise the server or other devices? And that also depends where this configuration security should be stored, which parts of the configuration are critical information, how scalable is the approach, what happens if the flow needs to be changed on when target device number drastically changes. Let's start here with the first question and 2 possible answers. So, when the actual process is going to happen? First one is remote provisioning. After the device is deployed and out of the factory, it uses some pre-provisioned data that allows for establishment of secure channel to the server, so that the device can be safely provisioned with final credentials that are going to be used for management. It allows for higher flexibility, but requires a secure channel for first connection. So mechanisms like IoT Safe are useful, as SIM cards come pre-provisioned already and can be used as a root of trust. After that, the EST, like enrollment over secure transport, can be used to generate certificates and share them between server and the device. An alternative to remote is the factory provisioning. So all the required credentials are written to the device at the factory. It also allows to do the final testing of the device before the deployment, but requires that the device configuration will be known from the beginning. It can be also done either by software or physically, so by uploading the credentials to the device or soldering in a hardware security module with the credentials. For the next topic, I'd like to talk a bit about lightweight machine-to-machine, as it would be easier to understand our solution this way. So it is a standard created by Oma SpecWorks. It specifies the device management, telemetry, and service enablement mechanisms for devices that have limited processing and storage capabilities. The data model in the lightweight machine-to-machine is organized in a three-level tree. First, we have objects that contain object instances, which consist of resources. So each level has its own numerical identifier, like here, for example, path /0/1/2 would mean that it is a resource ID 2 that is contained in the object instance 1, which is contained in object 0. So the biggest advantage of that approach is that there is this lightweight M2M registry that matches object IDs and describes what the actual content of the data is. So that way, server can communicate with any lightweight machine-to-machine device and be sure that data is consistent between different vendors. A comparable process to provisioning that is present in lightweight machine-to-machine devices is the Bootstrap interface. It allows for provisioning the lightweight M2M devices both remotely and in factory, as well from smart card. It has to be stated here that in the specification, only information about the factory Bootstrap that exists, and so it's not really helpful. And customers tend to improvise their own flows. So during our deployments, we've noticed common paths that could be useful also for non-L1-to-M devices, and decided to define them into a new flow that could be generic and allow for easy integration. Smart Card Bootstrap allows for something in between factory and remote provisioning. By initializing the device using data provided by Smart Card and extending it, so by using this mechanism and extending it to extract arbitrary data sources, not just smart cards, but keeping the format, we create a generic flow that can be used for different scenarios. At the diagram, we see two separated areas. One is the factory machinery where all the automation and scripts and flashing is done, and second is the actual device. So elements that are in yellow are provided as parts of general solutions, where gray elements are customs that need to be added for a specific solution. First element is the NJ provisioning tool. It generates CBOR blobs that contain provisioning data, and also it also communicates with the Coiote device management server. So it sends the data to the custom factory tooling so it can be done either by the Python calls or the command line interface tool. The factory tooling realizes the flashing and communication with the device, and the process starts with flashing the provisioning firmware onto the device. So factory tooling calls to the NJ provisioning tool with configuration, which then generates the CBOR blob that can be consumed by the device. And on the provisioning firmware side, there is a custom input handler that handles the communication between the device and factory machinery. It then passes on the CBOR blob to NJ factory provisioning module, which writes credentials to secure storage. So it can be like a hardware security module or trusted platform module. After the device confirms that to the factory tool that data has been successfully provisioned and saved, its configuration is uploaded to the Coiote IoT device management server. And then the device is flashed with application firmware that will, in process, erase any trace of unencrypted credentials from flash and later on use provisioned data from secure storage. So what is this tool and how it can be used? What can it do? Most basically, it generates encoded packets that are encoded in SNML CBOR. They contain basic object information, so any kind of information that is needed for provisioning. We can use signed certificates, or we can generate self-signed certificates using the tool. And it is also used for loading the configuration to device. Currently, we have a custom adapter for Nordic boards. and also for automatic device onboarding to the Coiote IoT DM platform. The main class of the library user will interact is the factory provisioning class. It takes a few different arguments. First one is the endpoint config. It is a path to the file with device configuration. And next parameter is the endpoint name, that is a unique name for each device that is used during registration. The server info is path to the file with Coiote server information. And the token parameter is used to authenticate the REST API calls. The last one is a cert info parameter that is used to pass the file containing information used generation of self-signed certificates, or can be used to pass already signed certificates. So what needs to be implemented on the factory side? Basically the whole script, the whole layer that is automating everything, and it just calls the methods from the factory provisioning tool. So it generates the factory tooling should generate custom configuration per device, take care of flashing the device and sending the SIBO data. All other things like encoding the data and provisioning it in a safe way are realized by the factory provisioning tool. Looking at the configuration path of the device, first is the server configuration. So this is the server that to which the device should be provisioned. It is not the actual server to which the device will connect. It is just information for the tool to which server should it call with the REST API and where should be all the data stored. So we just basically have the URL, port number, and domain under which the device will be put on. Second is the device configuration. As I was saying about the lightweight M2M data model, it can represent any object from the registry like APN or wireless LAN connectivity. So it is so the whole device configuration is expressed as lightweight machine-to-machine objects. So in this case, we see the security and server object, and this is the basic information on how to get to the management server. It can as well represent objects like said before, APN profiles, so that you can provide any SIM card information or wireless LAN connectivity, so any passwords to Wi-Fi, basically any also for LoRa connectivity. You can also store objects that are not related to connection, but related to the devices working, like sensor objects, etc., and pre-provision them with some data, so they could be configured like that. The file is in the format of a Python dictionary that is evaluated as a library, and it represents the objects to be loaded on the device. So if we want to generate certificates, we also need to add a certificate generation configuration. Here is basically the basic information that you get from the certificate and what should be put there. So of course we can use external certificates signed by certificate authority and not do it ourselves. So we just pass those to the script. How the actual configuration script would look like. So first we create an object of factory provisioning class, passing the arguments provided to the script. And depending on the security mode set in the endpoint config, we can generate a self-signed certificate or pass the paths to the certificate for both the client and the server. Next, we call provision device. That will load the configuration to the device. And finally, we can call register to automatically register the new device to the Coiote. We are, of course, register the device only if there were no errors previously. So we try to catch all the exceptions. If anything is going bad, the script shows error messages that should hint what is going wrong. And what needs to be implemented on the device side? In the provisioning firmware, there is already a NJ factory provisioning module that decodes the data and allows for reading them in a preferred way. So we need to implement the receiving of the SIBO data. basically just reading from UART or reading some preconfigured region in Flash, and integration with custom secure storage depending on what we plan on using in our application. How it integrates with Zephyr? Currently, we have demos for the Nordic devices. The whole approach is generic, so pretty much can be used for any device, but here I'm talking about the current state where we provide you a showcase on how it can be done. The example of provisioning flow is using the NJ Zephyr client. It can also be used with Transfer Firmware M. We are currently using the modem as a secure storage for the credentials, and there is an ongoing work in progress to support other roles. So what could be extracted to Zephyr? We think that it will be beneficial to just have an universal provisioning flow that would be made for all the devices in Zephyr available. So the provisioning data description is contained as is described by the lightweight machine-to-machine specification. It contains many objects, so pretty much anything can be written there in a structured manner. And the device does not have to be a lightweight M2M device, so we use the object registry only for the structure of the provisioning data here. Yeah, so that's the summary. We can use the registry to generate generic provisioning data. It doesn't have to be LWM2M devices to provision that. And with further integration with Zephyr, we could move from custom ports per device vendor and just unify the flow for all Zephyr devices. Currently, it is a work in progress, and we look forward to hearing from you. Here are some links to the topics I described. Here is the client and the module. Then there is the documentation on the tools and my LinkedIn if you want to talk after the event. Currently, I'll be here. And also the Discord server where you can catch with other guys from the AVSystem. So that's all for that part. And are there any questions? Yes.
It can be used with non-LWM2M devices. So we understand correctly that fast storage, for instance, LWM2M model would be used, store credentials to the local memory, and then applications viewer use those credentials, but they are not any longer in LWM2M format.
Yes, so the question was if we are using the LWM2M format, but the device is non-LWM2M, how would it be accessed? So that's correct, the second part of the question, that we use the LWM2M format only to generate the CBOR blob, and later on, as it is stored in the secure storage, it is no longer related in any way to LWM2M and can be used in any application. Is the CBOR proprietary? No, it's not proprietary. It's part of the LWM2M specification also.
Clarifying question. You're basically LWM2M ground, but not really the rest of it.
Yeah, it is possible to do that. Of course, mostly we focus on the LWM devices, so we just take straight from it and then, but still at the end in the device, we have to store it in some way, so.
So I noticed that you had a plain text key in the data that you sent through CBOR over to the device. Is that key plain text all along the way, or is it encrypted in some way? Because if you have an attacking entity in the factory, they will see the keys for all the devices that you're building.
Yeah, but then it's like, okay, so is the key encrypted in any way, or if attacker is in the factory, would it also be passed to the attacker? Yeah, so I'll be honest, I didn't thought about this way of attack. Like
you're building an
Okay.
IoT device, you have a third party doing the build. And if that third party is picking off all your keys for every device, then they can sell that data to a hacking society.
You did mention other ways.
Yeah.
Yeah, so okay, so still the question is the same. So basically, here is the assumption that in the factory we have the safe environment, and that's the like case where you just can send the keys and be sure that there is everything fine there. So in case where the factory is not a trusted place, we can just use the remote provisioning, and then we like generate only keys for the provisioning, and after the deployment or after receiving the part, we turn off the device, and then we use like it as the first root of trust, and then just use the environment of a secure transport to exchange the certificates and provide new data for the device.
Which increases the provisioning time for each device.
Yes.
Which if you're building tens of thousands a day could be bad.
Yeah, it would be bad.
Yeah, so another option for that would be the ASP mode and the device penetration. Using the third party.
Yeah.
So we just
Yeah. Yeah.
Third party manufacturers, they are completely offline. So they're not connected to the internet. Provisioning devices to the factory. Is anything in your flow change for an offline factory? I was assuming that for online or provisioning.
Okay, so the question is, if the factory is offline, what changes in the flow if we can get the credentials right to the platform? We can also generate like a CSV file with all the credentials for the devices, and then just upload them in bulk to the platform and have them provisioned there. So that's all, I think. Thank you so much.